We're looking at now for the rest of this packet are some of the other cardiovascular regulatory processes. So these are other mechanisms by which we can manipulate mean arterial pressure and we can manipulate things like our heart rate, our stroke volume, and total peripheral resistance, okay? And so we'll go through each of these one by one. So the first one is sinus arrhythmia or respiratory sinus arrhythmia. And this is really a response of our inspiration and expiration on the autonomic nervous system. And so basically when we inspire, when you take a nice big deep breath in, this has an increase in sympathetic activity, which actually increases heart rate. And when you expire, this has an increase in parasympathetic activity, which basically decreases our heart rate. And so it's not quite understood why this happens, but there are certain implications for this. So this is why we practice deep breathing as a part of meditation and relaxing the body, calming the body, is really to override the sympathetic response and to increase that parasympathetic influence, right? Taking nice, long expiratory breaths and then shorter inspiratory breaths. Another implication of this has to do with archers or any type of hunters, shooters even. They basically can capitalize on this response. So this is why they usually pull the trigger or, fire their target, their archer, their aim when they're in an expiratory phase of respiration. So basically the body is calm, it's stable, and there's less there's less likely to be shaking or jerking or missing that target when you take that shot during expiration, right? Because you're invoking that parasympathetic, that calming response. The second reflex or response here is the chemoreceptor reflex. And this has to do with a response to the amount of carbon dioxide levels in the blood. And so when we see increased levels of carbon dioxide in the blood, we basically have a response to increase our ventilation, okay? And so what we see is that there are two other responses here. There's a decrease in heart rate, and then there's an increase in total peripheral resistance. Now, these two changes seem contradictory as well as counterproductive, okay? So if I'm increasing CO2, this is a mismatch in the gas exchange. And so we would expect to see an increase in heart rate to get more blood flowing to the tissues. And so seeing a decrease in heart rate is somewhat counterproductive to that. But if you take a look at the perspective of the heart, a decrease in heart rate actually works to decrease the heart's demand for oxygen, okay? And so what this does is it decreases how much oxygen is required by the heart by decreasing that heart rate. And then a way to combat that response is by increasing total peripheral resistance, okay? So if we were to only decrease heart rate here, the response that we would see is a decrease in mean arterial pressure. We just talked about that relationship. Decreased heart rate would cause decreased mean arterial pressure. But because we also have this sort of combative response of increasing total peripheral resistance, we actually end up seeing an increase in mean arterial pressure. Okay, so let me say that here one more time. When we have increase in cardiac output, not cardiac output, when we have increase in CO2, carbon dioxide levels in the blood, the response is to decrease heart rate, which may seem to be counterproductive, right? Decreasing heart rate would actually decrease mean arterial pressure. But that decrease in heart rate is what works to decrease the heart's demand for oxygen. And then in concert with that decrease in heart rate, we also see an increase in total peripheral resistance, which helps to negate that otherwise drop in mean arterial pressure that we would see. And in general, the response we end up seeing is an increase in mean arterial pressure. Okay, I hope that makes sense. So this is a bit of a more complicated response, seems counterproductive, but it actually works from the standpoint of the heart. The third mechanism or response here is the thermoregulatory response, and this is mediated through the hypothalamus. And so it's our response to increases in body temperature or decreases. So we can think about this in both directions. But in the example of increasing body temperature, if you're overexerted, if it's a really hot day, body temperature rises, what we see is an increase is a decrease in sympathetic activity to the skin, which causes an increase in blood flow to the skin. So there's vasodilation of those arterioles going to the skin that causes more blood to flow to the skin, and that allows for more heat loss. So as more blood moves to the peripheral tissues, to the skin, we can lose some of that heat with that blood flow. And if we were to think about a decrease in body temperature, if you're extremely cold, if you're an extremely low body temperature, you would see an increase in sympathetic activity to the skin. That would cause vasoconstriction to the skin, and that would allow you to shunt more blood towards your core and keep your core, your internal, your deeper body structures and vital organs warm as a way to conserve that heat and prevent heat loss. Now, this thermoregulatory response is actually overrides or trumps or takes precedence over the baroreceptor reflex. And just to bring up the baroreceptor response here, we talked about that vasoconstriction being brought about on most of our arterioles as a way to increase total peripheral resistance and increase mean arterial pressure. So that's what we just described as a part of this baroreceptor reflex. Now, if you're exhausted, if it's a hot day, let's say you're working out, you're sweating a lot, the thermoregulatory response is going to take precedence over that baroreceptor reflex. In other words, you're still going to have vasodilation to your skin in order to lose that heat, whereas you would otherwise expect to see vasoconstriction, right? And most of that blood being shunted to your heart and muscles. The skin is one of those small exceptions here again. If you're really hot, the thermoregulatory response is going to take precedence over the baroreceptor reflex. And where we would expect to see vasoconstriction, we would actually see vasodilation to the skin. And so that would maintain that blood flow to the skin so that heat can be lost and we can keep the body cool, okay? And then, so the consequence that we would see of this is a decrease in total peripheral resistance and a decrease in mean arterial pressure because of that vasodilation that is shunting more blood to the skin to help cool the body. Okay. And then the final bit here really has to do with the response to exercise. We kind of touched on the response to exercise before, but this is a graph that shows how some of these volumes or these variables change with respect to their resting state. So when you're exercising, your blood flow to muscle increases almost 200 times or 200-fold what it would be at your resting state. Your cardiac output raises over 100-fold. Your heart rate raises over 100%. Stroke volume also raises. And then to a lesser extent, mean arterial pressure raises and end diastolic volume raises. Whereas we see a drop in total peripheral resistance, okay? And an interesting thing to point out is that the end diastolic volume doesn't raise that much. Can anyone predict why the end diastolic volume doesn't raise that much? Given some of the other variables that increase, why would we not see a larger increase in end diastolic volume? And just to reiterate, end diastolic volume is how much blood is filled into the ventricle to be ejected.
Is it because the heart is beating so much that there isn't enough time for it to fill?
Excellent, perfect, thank you. And that's absolutely correct. So the heart is filling more rapidly because the heart rate has now increased. And so there's not enough time for that filling, okay? And so we don't see as large a change in end diastolic volume as we do for, say, stroke volume or some of the other variables, because we actually sacrifice some of that filling time as we increase heart rate. So excellent conclusion to draw there as far as the change in end diastolic volume and how that compares to our heart rate and stroke volume change.